Good morning, everyone. My name is Adedotun Adeyemo. I am a research student from Oxford Brookes University, Oxford, UK. My presentation today is titled Analytic Models for Crossbar Write Operation. Although this work majored on Memristor-based crossbar array, similar analysis can, however, be directly mapped to crossbar arrays with similar two-terminal devices. Before I proceed, I will give a brief outline of what I will cover in this presentation. I will give a brief motivation for this work, followed by a brief introduction to Memristor, just in case there are people in the audience who are hearing about the device for the first time. This will be followed by an explanation of the crossbar architecture itself and its equivalent resistance model. Then I will go on to explain three of the existing techniques for writing into crossbar memories. These schemes will be further analyzed with and without the presence of wire resistance before I conclude the presentation. One of the motivations for this work was the demand placed upon the semiconductor industry and the academia as a whole by the ITRS. ITRS is the International Technology Roadmap for Semiconductors. Most people in the semiconductor industry or anyone working with transistor acknowledge that it's becoming increasingly difficult to scale the transistor beyond its current size. For this reason, a number of technologies have emerged in recent years. Memristor is just one of these technologies. Memristors have applications in artificial neural network, logic gate design, among many others. This work, however, focuses on its memory application. Memristor is highly rated and has been tipped to usher in a new generation of universal memory that can combine the benefit of existing memory technologies such as SRAM, DRAM, and flash drive. Now to the Memristor device itself. Memristor is a two-terminal passive element. It was first discovered by Leon Chua in 1971 based on symmetrical arrangement of the four variables of electrical circuit. And the variables are charge, voltage, current, and magnetic flux. With this arrangement, there are 6 unique combinations from these variables, and the only one of this relationship was missing as of 1971, which is the relationship between charge and flux. Chua named the relation memristance and coined the name memristor, a portmanteau of memory and resistor, or better still, a resistor with memory. The work of Leon Chua was, however, all theoretical based and was left for decades until 2008. In the year 2008, the first public realization of a physical memristor was announced by scientists at HP Labs. Research and other development activities on Memristor have since increased exponentially. HP Labs Memristor was made of titanium dioxide, which was sandwiched between 2 platinum electrodes, as can be seen on the screen. So a portion of the titanium dioxide was doped, which makes the conductivity quite high. The doped part of the device has a low resistance, while the undoped region have a high resistance value. With this structure, the fabricated device can switch between 2 unique states when used in memory application. The logic state 1, which is the low resistance state, or the RN, as we can see from the equivalent circuit on the right hand side, or the logic state 0, which is the same as the high resistance state, or ROF. This is the reason why memristor represents data as resistance, unlike charge in transistor-based memory. The equation below represents the memristance over a given time. This equation was coined by the same scientists at HP Lab to represent the behavior of the memristor. It is dependent on the value of R1 and ROF, as well as time-dependent state variable W, which indirectly act as a barrier between the doped and the undoped region in the device. It's a variable barrier because it moves as voltage is being applied to the device. D in the equation is the weight of the device, and that basically explains the physical structure of the memristor. Here we talk about the I-V characteristics of the memristor, which sort of explain how it operates in its basic form. Memristor changes based on the magnitude and polarity of the applied voltage. In this I-V curve, a positive voltage switches the memristor from high resistance state to low resistance state, or better still from state 0 to state 1, and negative voltage switches it the other way around. The magnitude of the voltage should be greater than the threshold voltage of the memristor in order for the memristor to switch states. And in this same image, the grayed out region in this figure represents the voltage range where the state of the memristor remains preserved, and this state can be used for reading or probing the memristor. Having clearly established how the memristor operates, it is worthy of mention that a single memristor on its own is not much of a use in memory application except they are combined into an array of memristors. As you can see from this image, the crossbar architecture consists of parallel set of horizontal and vertical nanowires. This set of parallel nanowires are thus placed perpendicularly on each other. So I'm just explaining how the crossbar is being designed. A memristor is thus inserted at every cross point of each pair of perpendicular nanowire to result in a memristor-based crossbar architecture. A fully memristor-based architecture is depicted by the figure above. With this, highly dense memory structure can be designed and made applicable in everyday computing. As regards the modeling of the crossbar array, so let's assume the memristor circled in red is selected for read or write operation. The overall equivalent resistance model of the crossbar array can be simplified to this little image on the right hand side. In the equivalent socket, rselect or RSEL, like I named it, is the selected cell, which is the resistance of that memristor that has been selected for write or read operation. RM, RMN, and RN are the parallel combination of the other groups of non-selected memristor in the crossbar. Each of these resistance can be represented by the following equations. Depending on the value stored by the memristors, that determines the equation that will represent each of these resistance value. More information about these equations are detailed in the main paper related to this work. Since this work focuses more on the write operation on crossbar array, here we talk about the major conditions that must be satisfied for the write operation to be termed successful, assuming all other external and negligible factors remain favorable. The first condition that must be satisfied is related to the selected cell, which is quite obvious because that's the cell we want to write into. The state of the selected cell must switch to the desired value depending on its current state, either from a logic 0 to logic 1 or from a logic 1 to logic 0. The second condition relates to the other non-selected cells. The state of the non-selected cells must remain constant for the entire duration of the write operation. The write operation will fail if one or both of these conditions fails. So in order to satisfy both of these conditions, a number of write techniques have been proposed in literature. I'll be talking about 3 of the existing techniques on the next slide. The first scheme here is the floating scheme, which we've used to model the crossbar on previous slide. The 2 other schemes are 1/2 and 1/3 biasing scheme, as can be seen on the screen, and I have the equivalent resistance model on the right hand side of each of these schemes. So the major structural difference between these schemes is the voltage being applied to the non-selected cell. In the floating scheme, it's left floating, and in the 1/2 scheme, it's being biased by voltage by half of the voltage on both the bit line and the word line, while on the 1/3 scheme is being biased by 1/3 voltage on the word line and biased by 2 multiplied by the write voltage divided by 3 on the bit line. This is to ensure that the voltage across each of these non-selected cells does not exceed V/3. The 3 schemes work perfectly with negligible wire resistance, except for floating line scheme that could be unpredictable as array size and the aspect ratio of the array size changes. Of these 3 schemes, floating scheme consumes the least power for obvious reason because we have less voltage rail. What we did was to investigate the constraint that might make the floating scheme desirable in order to take advantage of its low power consumption and reduce the unpredictability of the voltage drop on non-selected cells as array size varies. On this slide, I have a simulation result of the voltage drop on the non-selected cell using the floating line scheme. There are 3 cells on these figures. Each one represents each group of non-selected cell. The purple curve represents the voltage on the unselected cell on the selected word line. The green curve represents the voltage on the unselected cells on the selected bit line, while the blue surf represents the voltage on the unselected cell on the unselected lines. If you look at this figure carefully, you will notice that points where M is equal to N have a voltage drop not exceeding 50% across the three groups represented by each of those surfs. But as M and N begins to deviate from each other, the voltage disturbances to the unselected cell increases and could be up to 100% on partially selected cells. The partially selected cell are the cell on the word line and the bait line that are unselected. This experimental result shows that disturbances to non-selected cell does not exceed 50%, which is half of the right voltage, as long as the crossbar structure is of a square size. That is, M is the same as N, the weight is the same as the height. This means that we can take advantage of the low power consumption of the floating line scheme by ensuring the weight and the height of the array remains equal. And this table just gives a summary of the performance of the three right scheme across various parameters. So I will concentrate just on the third row of this table. If you look at the equations in there, you will realize that it's only the floating line scheme that have a voltage drop on selected cell that is dependent on the array size M and N, which is the reason for its deficiency, which we have managed to constrain by ensuring the array have similar width and height, as I discussed previously. The other two schemes are not dependent on the array size in any way. The voltage drop on the selected and non-selected cell remains the same irrespective of the array size or structure. Now we move on to write operation in crossbar array with full consideration for the effect of line resistance. So all along we've assumed negligible line resistance. However, in larger arrays, the effect of line resistance cannot be ignored. The behavior of all the three schemes that was described earlier changes in the presence of line resistance. I'll use the word line and wire resistance interchangeably. The image on this screen shows the resistance model of a typical crossbar array, where there is a corresponding wire resistance adjacent to every memristor in the crossbar array on both its bit line and word line. The effect of this resistance is felt on selected cell as it receives less voltage from the voltage driver due to voltage decay caused by wire resistance as the voltage travels from its source to the destined cell. The larger the crossbar size, the more the effect of wire resistance. So that means cells that are farther away from the voltage source will experience much more less voltage. This means that voltage farther away from the voltage source will receive lesser voltage than was intended. Here I have the simulation result, which shows the voltage drop across selected cell and non-selected cell over a range of array sizes using each of the three previously explained write techniques. This result shows that as the array size increases, the reliability of the write operation reduces. You could also notice that for some array size, the voltage disturbance actually exceeds the voltage reaching the selected cells. The memory is pretty much less useful at this stage because a failure will occur at every point in time. That is, we have less voltage reaching the selected cell that is insufficient to switch it to the desired state, and we have more voltage reaching the non-selected cell, so the disturbance is pretty much higher than the voltage reaching the selected cell. For the purpose of this simulation, we've assumed a worst case scenario where all cells in the array are in low resistance state, and we've also used a worst case line resistance value of 0.1 ohms. I'll give a quick summary of this work before I conclude this presentation. Ideally, the 1/2 and 1/3 biasing write scheme produce predictable and acceptable performances without line resistance irrespective of array size or aspect ratio, but they consume more power than the floating line scheme. And as I said earlier, the floating line scheme can be made effective as well by ensuring the aspect ratio of the crossbar is a square one, that is, the weight is the same as the height. This way, designers can benefit from its power conservation. I also showed that with worst case wire resistance, all the write schemes are limited in the designing of high density memories because line resistance can always trigger write failure in larger array. So for the purpose of this work, the analytic model for crossbar array that we presented in this work, they were all verified by comparing our experimental result, or better still our analytical result, against simulation result using the Cadence Spectral simulation tool. Thank you all for listening. If you have any question, you can kindly send me an email on the address above. Thank you.